Right now, on the most distant planet in our solar system, winds are tearing across the atmosphere at nearly 4 times the speed of the strongest hurricane ever recorded on Earth. Temperatures out there should be predictable, locked into a slow, multi-decade seasonal rhythm that scientists thought they understood. Instead, over the past 2 decades, this planet's atmosphere has been swinging through changes nobody expected, cooling when it should have been warming, then snapping back with a violence that has left researchers openly admitting they don't have a full explanation. Something is happening on Neptune, and the honest, unsettling truth is that the people who study this planet for a living are still trying to figure out exactly what it is. Neptune has always occupied a strange place in the story of our solar system, because it wasn't discovered by accident. It was discovered by mathematics, before a single human eye ever confirmed it existed. In the early 1800s, astronomers noticed something wrong with the orbit of Uranus. It kept drifting slightly away from where careful calculations said it should be, as if some invisible hand were tugging on it. 2 mathematicians working independently, one in England and one in France, both reached the same conclusion. An undiscovered planet had to be out there, its gravity quietly bending the path of its neighbor. The French astronomer sent his calculations to an observatory in Berlin, and on a September night in 1846, a German astronomer pointed his telescope at the precise coordinates that had been predicted on paper alone. There it was, a small, unmistakably blue point of light, exactly where the math said it would be. It remains one of the most striking moments in the history of astronomy, a planet found not by searching the sky, but by trusting the numbers. They named it after the Roman god of the sea, a fitting choice given its deep, otherworldly blue color, visible even through the primitive telescopes of that era. But for well over a century after that dramatic discovery, Neptune stayed almost entirely hidden from real scrutiny. Every telescope pointed at it through the 1800s and well into the 1900s showed little more than a smooth, featureless blue disk, too distant and too faint to reveal anything meaningful. Neptune sat there for generations, a confirmed planet that nobody could actually study in any real detail. That finally changed in the summer of 1989 when NASA's Voyager 2 spacecraft reached Neptune as the final stop on its grand tour through the outer solar system. It was a brief encounter, just a handful of hours of close contact after a journey that had taken 12 years. But in those few hours, everything we thought we knew about this planet was rewritten. Voyager 2 sent back images of a violently active blue world, streaked with massive storm systems, laced with white methane clouds, and dominated by something researchers named the Great Dark Spot, a storm roughly the size of planet Earth itself. That storm later vanished completely, and it has never reappeared in the same location since, as if the planet simply swallowed it whole. Neptune's atmosphere is made up mostly of hydrogen and helium, laced with a small amount of methane, and it's that methane doing all the work behind the planet's famous color, absorbing red light from the sun and reflecting blue light back out into the darkness of space. But the color is almost the least unsettling part of this planet. What actually defines Neptune is its weather, and calling it extreme barely covers it. This is the windiest planet in the entire solar system, with gusts reaching speeds up to nearly 3,900 miles per hour. A Category 5 hurricane here on Earth, the kind that levels coastal towns, would look like a lazy summer breeze by comparison. And here's the part that should genuinely unsettle you. Nobody fully understands how this is even possible. Neptune sits so far from the sun that it receives only a tiny fraction of the solar energy that reaches Earth. There simply shouldn't be enough external energy available to power winds of that magnitude. Researchers suspect the planet's own internal heat plays a major role, since Neptune somehow radiates more than twice as much energy back out into space as it actually receives from the sun in the first place. Something hot, something active, is clearly happening deep beneath that thick, churning atmosphere, and we still don't know exactly what. Neptune's magnetic field only deepens the strangeness. It's powerful, but it's tilted at a bizarre angle, roughly 47 degrees away from the planet's actual rotational axis, and it isn't even centered on the planet the way you'd expect. It's noticeably offset, shifted off to one side in a configuration scientists haven't observed on any other planet in quite this form. Imagine a compass that doesn't just point slightly wrong, but is mounted crookedly and shoved off-center inside the device itself. That's essentially what Neptune's magnetic field is doing, and it hints at something deeply unusual happening in the planet's hidden interior. No other planet we've studied up close behaves quite this way, which is exactly why researchers keep returning to this one detail whenever they try to model what's actually churning beneath Neptune's surface. Beyond the planet itself, Voyager 2 revealed a system of moons that turned out to be almost as strange as Neptune's atmosphere. By far, the largest is Triton, and Triton is genuinely one of the odder objects in the entire solar system. It orbits Neptune backwards, moving in the opposite direction to the planet's own rotation, a clear sign that it didn't form alongside Neptune at all. It was captured later, almost certainly a former resident of the distant, icy Kuiper Belt, the same frozen region that Pluto calls home, pulled in and trapped by Neptune's gravity and forced into an orbit that fights against the planet's own spin. Triton also turned out to be geologically alive, with Voyager 2 spotting geysers of frozen nitrogen erupting several kilometers into its thin atmosphere, clear evidence of what scientists call cryovolcanism, essentially icy eruptions driven by frozen material instead of molten rock. Despite everything that brief flyby revealed, no spacecraft has ever gone back. No orbiter, no lander, absolutely nothing. The most distant true planet in our solar system has remained for more than 3 decades now, almost entirely unexplored, simply because reaching it is so extraordinarily difficult and expensive. Even Voyager 2, using near-perfect gravitational assists from Jupiter and Saturn along the way, needed 12 full years just to arrive. A dedicated modern mission would require decades of planning, billions of dollars in funding, and an enormous amount of patience. But the scientific reward waiting out there could be enormous, because Neptune isn't just some distant curiosity. It's essentially a time capsule from the early solar system, and a direct window into an entire category of planet that has turned out to be remarkably common throughout the galaxy. Neptune belongs to a specific planetary category called ice giants, along with its neighbor Uranus, distinguishing both of them from Jupiter and Saturn, which are considered ordinary gas giants. The real difference comes down to composition. Jupiter and Saturn are made overwhelmingly of hydrogen and helium, but Neptune contains a much larger proportion of heavier elements, particularly water, ammonia, and methane. At the frigid temperatures found this far from the Sun, these compounds exist largely in frozen or semi-frozen states, which is where the name ice giant actually comes from. That doesn't mean Neptune is literally a giant ball of ice, though. The pressures and temperatures buried deep inside the planet are so extreme that these materials exist in genuinely exotic states we simply don't encounter naturally anywhere here on Earth. Beneath that violent, storm-streaked atmosphere lies what scientists call the mantle, an enormous layer of hot, dense material made of water, ammonia, and methane, existing in an exotic state somewhere between liquid and gas. Researchers suspect this layer may contain an unusual form of water known as superionic ice, in which hydrogen ions move freely through a rigid lattice of oxygen atoms, functioning almost like an electrical conductor operating under crushing pressure and extreme heat. This bizarre layer may be responsible for Neptune's strangely tilted off-center magnetic field, though for now that remains a working theory rather than a confirmed explanation. Deeper still sits what's likely a rocky, metallic core, buried under pressures millions of times greater than anything found at Earth's surface, so extreme that even the hardest known materials would exist in a state scientists still struggle to fully predict or model. What's actually happening down there, at the very heart of this planet, remains genuinely speculative. This matters for reasons that go well beyond simple curiosity about one distant planet. Over the past 2 decades, astronomers have discovered thousands of planets orbiting other stars, and a significant number of them fall into a size and mass range remarkably similar to Uranus and Neptune, larger than Earth, but smaller than Jupiter. This entire category of world appears to be extraordinarily common throughout the galaxy. Neptune isn't some unusual outlier sitting alone at the edge of our solar system. It's essentially a nearby, accessible example of one of the most common types of planet in the entire universe. Understanding how it actually works, its internal structure, its violent storms, its unexplained heat source, could meaningfully improve our understanding of countless similar worlds scattered across the galaxy that we will likely never be able to visit directly ourselves. Neptune also carries a full system of moons and rings that tend to get overlooked. They deserve real attention, too. The planet currently has 16 confirmed moons, and Triton alone accounts for more than 99% of all the mass orbiting Neptune combined. Triton isn't just orbitally unusual either. It's genuinely alive geologically, one of only a handful of confirmed geologically active bodies anywhere in the solar system, joining a very short list that includes Jupiter's moon Io and Saturn's moon Enceladus. That's remarkable, given how far Triton sits from the Sun, with a surface temperature hovering around negative 235 degrees Celsius. Despite that brutal, unforgiving cold, something is clearly active beneath the surface, possibly driven by tidal forces from its slightly elliptical orbit, or by the slow decay of radioactive elements deep inside, or some combination of both working together. Some researchers have even proposed that Triton could be hiding a subsurface ocean of liquid water beneath its icy crust, similar to what's suspected on Jupiter's moon Europa or Saturn's moon Enceladus. If that turns out to be true, Triton wouldn't just be a geological curiosity anymore. It would become a genuine candidate in the search for life beyond Earth, hidden deep beneath the ice, sealed away in permanent darkness, far from any sunlight at all. Beyond Triton, Neptune hosts a scattering of smaller moons, many of them little more than irregular captured fragments. Nereid follows one of the most elongated, stretched-out orbits of any moon in the solar system. Proteus, the second largest of Neptune's moons, is an oddly shaped, heavily cratered chunk of rock. Then there are the tiny inner moons orbiting close above Neptune's cloud tops, likely remnants of earlier collisions between larger moons that broke apart, sometime in the ancient past. That same inner region is threaded with a faint ring system that often gets completely overlooked. Like Saturn, Neptune has rings, though considerably fainter, darker, and far harder to detect. For years, their existence was only suspected, based on brief moments when Neptune passed in front of a distant star and caused a telltale dimming. Voyager 2 finally provided direct visual confirmation. The rings are made mostly of dark dust and rocky debris, likely material released during past collisions between small moons, arranged into 5 main rings, the best known carrying names honoring the 2 astronomers whose mathematics first predicted Neptune's existence in the first place. One particular curiosity involves clumped sections of ring material known as ring arcs, dense concentrations of debris that appear as unusually bright segments rather than being evenly spread around the ring the way ordinary orbital mechanics would normally predict. Now, for the part that's genuinely confusing researchers today, and the reason this distant, frozen world deserves your full attention right now. In 2022, the James Webb Space Telescope turned its infrared instruments toward Neptune and captured the clearest images of its ring system in more than 3 decades, the sharpest views obtained since Voyager 2's brief flyby back in 1989. Because James Webb observes in infrared wavelengths, it can effectively see through the dust and gas that would otherwise obscure fainter detail, revealing structure that ground-based telescopes and even Hubble had struggled to capture with the same clarity. A Neptune specialist involved with the James Webb team noted that it had been 3 decades since these faint, dusty rings had last been seen this clearly, and this was the very first time they had ever been observed specifically in infrared light. The image doesn't show Neptune in its familiar vivid blue, since methane strongly absorbs red and infrared wavelengths, leaving the planet looking comparatively muted and gray in James Webb's infrared view, aside from bright patches where high-altitude methane ice clouds catch and reflect sunlight before it gets absorbed. But the true scientific value here has nothing to do with color. It's about the level of structural detail suddenly visible in the rings, in several of Neptune's moons, and in a faint band circling the planet's equator, that researchers have linked to a global atmospheric circulation pattern shaping weather movement across the entire planet. And that discovery leads directly into the part that should genuinely give you pause. Right now, Neptune's southern hemisphere should technically be moving through its early summer season, meaning temperatures out. There should be gradually rising in a slow, predictable seasonal climb. Instead, researchers have documented a substantial, largely unexplained temperature drop across the entire planet. A study analyzing 17 years of temperature observations found that Neptune's globally average stratospheric temperature dropped by roughly 8 degrees Celsius between 2003 and 2018, based on a clear, measurable decline in the planet's atmospheric infrared brightness beginning around 2003. The scientist who led this research has stated plainly that the change was unexpected, since Neptune was being observed during its early southern summer, precisely when temperatures should have been slowly rising rather than falling. What's actually driving this unexpected cooling remains genuinely unclear. Researchers suspect it's connected to chemical processes happening deep within Neptune's own atmosphere. Methane absorbs sunlight and warms the atmosphere, while photochemically produced hydrocarbons, mainly ethane and acetylene, act as powerful infrared emitters that cool the stratosphere instead. In other words, subtle shifts in the balance between these specific atmospheric compounds can meaningfully change how much heat the planet radiates away into space, and therefore how warm or cool it registers overall. Similar chemical interactions affecting atmospheric temperature have previously been documented on Saturn as well, but seeing this scale of unexplained swing on Neptune caught researchers off guard. One possible contributing factor involves Neptune's massive, ever-shifting storm systems. The Great Dark Spot itself vanished back in 1994, but new storms of comparable scale keep forming unpredictably across the planet, and the underlying mechanism driving Neptune's storm formation still isn't well understood. It's entirely plausible that these storms disrupt or accelerate atmospheric chemical reactions in ways that could trigger unexpected cooling, even during a season when warming would normally be expected. Researchers have also proposed that Neptune's response to the Sun's roughly 11-year solar activity cycle might play some role, potentially triggering photochemical shifts in the atmosphere that could help explain the observed temperature swings, though this particular connection remains tentative and requires further observation before anyone can confirm it. And here's the detail that makes this whole story feel genuinely unsettling rather than just academically curious. This cooling trend reversed sharply after 2018, Neptune's temperatures snapped back upward within just a couple of years, rising by roughly 11 degrees Celsius on average, essentially undoing more than a decade of cooling in a fraction of the time it took to occur. That kind of rapid reversal on a planet this large and this far from any obvious external trigger is not the sort of thing a stable, well-understood atmosphere is supposed to do. Neptune's atmosphere, in other words, appears to be swinging through genuinely dramatic mood changes that don't line up neatly with its expected seasonal calendar at all. The lead researcher on this work has summarized the situation by noting that it points toward a genuinely complicated picture of Neptune's atmosphere and how it changes over time. And that part of what makes Neptune so fascinating to study right now is simply how little we still understand about what's driving these swings. Given how long it's been since Voyager 2's brief visit, it's worth asking what might finally change that, because several mission concepts are currently in various stages of development, aimed at finally sending something back to Neptune after more than 3 decades of silence. The most immediately plausible is called Triton, a mission concept proposed to NASA as part of its Discovery program. Triton would be a relatively lean, focused spacecraft, not an orbiter and not a lander, but a single, carefully targeted flyby of Triton, equipped with a high-resolution camera, a magnetometer, and several other scientific instruments. The mission's focus on Triton makes sense given everything already covered here: its backward orbit, its confirmed geological activity, and the real possibility of a hidden subsurface ocean, all packed into a moon far stranger than most people would ever expect this far from the sun. Depending on launch timing, the mission would take roughly 13 years to reach Neptune, meaning arrival sometime in the 2030s, possibly stretching into the 2040s, passing within roughly 500 miles of Triton's surface, considerably closer than Voyager 2 ever managed. A considerably more ambitious concept is Neptune Odyssey, a proposed orbiter mission designed to study Neptune over the course of many years rather than during a single brief pass. Odyssey would examine not just Triton, but the entire Neptune system, its rings, its atmosphere, its magnetic field, and its full collection of moons up close over an extended period, broadly comparable in ambition to NASA's long-running Cassini mission at Saturn. Beyond serving as an orbiter, Odyssey's design includes plans for a dedicated atmospheric probe that would descend directly into Neptune's dense, stormy gas layers, providing the first ever direct measurements from inside an ice giant's atmosphere, covering temperature, pressure, chemical composition, and the processes responsible for Neptune's extreme weather and its still unexplained heat output. Current planning envisions a launch sometime between 2030 and 2035, with arrival at Neptune not expected until the 2050s. It's a long, expensive, and technically demanding proposal, but if it moves forward, it would represent one of the most significant achievements in outer planet exploration to date. There's also a genuinely inventive concept called the Triton Hopper, which sounds almost like science fiction. Rather than landing in one fixed location, this mobile lander concept would move across Triton's surface by literally hopping from place to place, using the moon's own surface nitrogen ice as fuel, heating it to generate a jet of gas capable of launching the lander back into the air for its next short hop. In theory, the hopper could make dozens of these jumps, covering meaningfully large distances, and allowing researchers to study multiple regions, including Triton's strange cryogenic geysers, its surface fractures, and its icy plains, rather than being limited to a single landing site. It remains highly experimental and still in an early stage of development, but it illustrates just how much creative engineering potential exists for exploring this distant, strange little moon properly. So here's where all of this leaves us. A planet discovered through pure mathematics before anyone ever saw it, winds faster than anything else in the solar system, powered by a heat source we still can't fully explain, a magnetic field tilted and shoved off center in a way we've never observed anywhere else, a moon orbiting backwards, erupting ice into space, possibly hiding an ocean in total darkness, rings that shouldn't clump the way they do. And now, on top of everything else, a temperature record that flips upside down without warning, defying the season it's supposedly moving through, a swing large enough that researchers who have spent entire careers studying this planet are openly saying they didn't see it coming. Right now, the most distant planet in our solar system is doing something scientists fully admit they cannot completely explain. And the only honest answer anyone can give you is that we won't really know why until something finally goes back out there to look closely enough to find out.